close a chat, the session ends, and the agent forgets everything you just discussed. Start a new task, and you have to introduce yourself and your preferences all over again. To fix this, we have to split how an agent remembers into two distinct parts. The first is short-term memory. Think of this as an open notebook on the agent's desk. It holds the active context of your current conversation, but the moment you walk away, that notebook closes. The second part is long-term memory. This is a permanent filing cabinet against a wall. It stores durable facts, user preferences, and prior decisions that survive long after any single chat window is closed. This diagram shows those two systems side by side. The left notebook is built for right now. The right cabinet is built for forever. Operating in parallel with LangGraph allows an agent to follow active instructions while maintaining a durable profile of your long-term preferences. If you learned how to build memory a year ago, you likely reached for classes like ConversationBufferMemory. Those older methods are officially deprecated. In 2026, the LangGraph standard splits memory into thread-scoped checkpointers for short-term recall and store-scoped vector databases for long-term retrieval. Implementing this architecture requires two distinct software mechanisms with separate configurations. The checkpointer manages the temporary state of active conversation threads, while the vector store handles the persistent filing and indexing of semantic data. Keeping the active notebook strictly separated from the permanent cabinet ensures your agent only reads what it needs. This protects the system from stuffing entire conversational histories into a single prompt, allowing it to scale safely without massive token costs. Step 1 is the build setup. We bring in two key models. The chat model handles reasoning, and a separate embedding model translates raw text into mathematical meaning. We are using OpenAI's Text Embedding 3 Small. It turns any sentence into a vector of 1,536 individual numbers. Because the model automatically normalizes these vectors to a length of 1, calculating similarity later on requires only a fast, cheap math operation. With our models ready, we wire up the short-term notebook. We do this by assigning a checkpointer object directly to the compiled LangGraph agent. But that checkpointer will sit completely dormant until you give it a specific key. To recall the active conversation, pass a unique thread ID every time you invoke the agent. Invoke the agent with a completely new thread ID, and the agent draws a blank. The notebook is strictly scoped to one conversation. This hard boundary perfectly protects active sessions from bleeding into one another. But if we want facts to outlive the thread, we have to build our secondary system. Now, step 2 is the filing cabinet. We give the agent a store object, and crucially, we define an embedding index. This allows the cabinet to organize information by its actual meaning, rather than exact text. You must set the index dimensions in the store to exactly match your embedding model. We used a model with 1536 dimensions, so we configure the store with 1536. If these numbers misalign, the entire index fails. Look at the right path. When the agent notices a fact worth keeping, it hands the raw text to the embedder. The embedder returns a point in meaning space. The store then groups that factor with the original text and files it into a specific namespace. Once the card is filed in that semantic space, it is secure. The active conversation can end, the session can close, and that preference remains completely durable. Now we test the recall. We start a fresh thread and ask what we'd like to drink. Notice we never use the word coffee. This diagram tracks the recall path. The new query passes through the embedder, mapping our question into the same 1,536-dimensional space. The system measures cosine similarity against every card in the drawer. It finds the closest neighbor, the coffee card, and pulls it out. A traditional keyword search looks for overlapping letters and would return nothing here, because the word drink and the phrase black no sugar share 0 common words. By searching in meaning space instead, the correct card wins. To increase accuracy, generate multiple phrasings of the user's question and search for all simultaneously. This multi-query approach covers a wider area of the meaning space, lifting recall rates by 30%. We are not storing memories just to hold them. Long-term memory is entirely a retrieval operation, finding the right card exactly when it matters. This is the complete architecture in motion. An input arrives. The agent reads the short-term notebook for immediate context, searches the long-term cabinet for past facts, reasons over both, acts, and then files any durable new cards back into the cabinet. We built this using temporary in-memory components, but the framework is modular, allowing you to swap those out for real databases in production. To protect the notebook against restarts, replace the memory saver with a durable backend like Postgres Saver. For the long-term cabinet, match your vector database to your scale. Use Chroma for local development. For SQL infrastructure, choose pgvector. For massive scale, migrate to Pinecone. Because the core loop remains completely isolated from the database backend, your agent can scale from a lightweight prototype to a massive cloud deployment without rewriting logic. Effective agent memory requires two distinct disciplines: file new information selectively, and retrieve only the cards that are mathematically relevant to the active conversation. Attempting to paste a user's entire history into a single prompt is a dead end. It degrades reasoning and scales your computational costs exponentially. Building a capable agent means trusting the retrieval system. You build the notebook for right now, the filing cabinet for forever, and you give your AI the architecture to forget the noise and retrieve only what matters.